Hi guys, so here I come again for more simple harmonic motion. So this is the second lesson and is about the principles of simple harmonic motion. So a little bit more than the basics. Again, there's going to be a playlist about all that stuff. So just go on the playlist, go on videos that say simple harmonic motion if you need to get some background information for what I'm telling you, okay? So first of all, there is a video that I'm going to put in the link in the description actually. So I'm going to put the link of the video in the description, which tells you one of the main principles about simple harmonic motion. You're going to have a pendulum wave. So that means that you're going to have many different masses. They are going to be golf balls. And they are at different lengths. They are all next to each other, but they have different lengths. So the strings have different lengths, okay? And we all start the same masses at the same time, but you will see that the masses will not oscillate with the same frequency. And this means that the frequency of the oscillations is going to depend on the length of the string. Not on the masses, but on the actual length, okay? And you're going to see different shapes that this does, okay? So that's very visual for you to memorize that or to understand that. And the string length represents the wavelength of the pendulum. So imagine that you attach then a paintbrush, for example, to the masses. You would get a wave like this one, a sine or cosine, okay? The string length would represent the wavelength of the pendulum, and the frequency, as you know from science before, it depends on your wavelength, because the frequency is the number of waves that pass a certain point in a second, so it is controlled by the wavelength. In this case, the wavelength is the length of the string. So that means, and what I'm saying so far is that if you have a different string, a different length of the string, then the frequency of the oscillations for your simple harmonic motion is going to differ as well, okay? So that's going to be very visual in that video. Other things that I'm going to tell you. So you have the oscillating object, right? So it's always going back and forwards, passing through an equilibrium position. So any oscillating material is going to speed up as it returns to the equilibrium position, okay? And it slows down as it moves away from the equilibrium position. And then I have here three graphs: the displacement, the velocity, and the acceleration time graph. And this is, if I would pick, for example, the pendulum, just like in the last slide, and I would have, for example, a paintbrush that would show how the motion would change in time, and this would give me either sine or cosine wave, right? So my first graph here is a displacement time graph, and the variation of the velocity with time is given by the gradient of this graph, okay? So with the gradient of the displacement versus time graph. Then I have the velocity time graph. If I want to know the variation of acceleration, that's going to be given to me by the gradient of this graph, so the velocity time graph. This is just like when we did other graphs, distance time graphs, velocity time graphs in GCSE. So this is just applying exactly the same to a different type of motion, where instead of having maybe a straight line, I have a constant curved line or a constant wave line. So again, a sine or a cosine wave, okay? And notice here in the acceleration time graph that the acceleration is always opposite to the displacement. Which makes sense, okay? Because my object is going to speed up as it goes towards the equilibrium. So as my displacement gets smaller, I am speeding up because I'm getting closer to the equilibrium. And as my displacement is going to increase, then my acceleration is going to decrease because my object is starting to slow down. And that's what makes it then reverse the direction and go back towards equilibrium, okay? More on the same graphs. So now getting to know the maximums and the minimums for velocity and acceleration. The magnitude of the velocity, and I say the magnitude because remember that velocity is a vector, so it means it has a number, which is the magnitude, and the direction. So the velocity is higher in terms of numbers when I have the gradient of the displacement time graph to be greatest, right? Because that's where I get the velocity from that graph. And this is when I'm meeting the zero displacement, okay? So when I'm at zero, at equilibrium. That's when I have the higher kinetic energy. And then the velocity is 0 when the gradient of the displacement versus time graph is going to be 0. So that happens at maximum magnitude of displacement. So here is when my velocity is going to be 0, okay, and you can see that here, okay. So at the maximum displacement, my velocity is going to be 0. My velocity is maximum as I pass through equilibrium. So as my displacement is 0, okay. So that's the explanation of what happens to the velocity. The acceleration. Now, the acceleration is greatest when the gradient of the velocity time graph is at greatest, okay? So when the velocity is 0. And this is at maximum displacement in the opposite direction. Now, as you can imagine, this is not exactly happen at that very second, right? Because I'm first starting to change velocity, so that's when my acceleration starts to get bigger. And you can even see here in the graphs, okay? And then my acceleration is going to be 0 when my the gradient of my velocity time graph is 0. So that happens when the displacement is 0, here we go, and when the velocity is at maximum. Again, of course, there's like some milliseconds in between these things, but that's what happens, and the graphs are going to show you very well, okay? Now, we are going to start focusing on the acceleration in simple harmonic motion. So I'm going to tell you the basics of the acceleration in simple harmonic motion. The acceleration is always proportional to the displacement. And then the acceleration is also always in the opposite direction to the displacement, as we saw already. So knowing points 1 and 2, I can say that my acceleration has this general formula, which is minus, because of opposite direction, constant, because it's proportional, times displacement. So acceleration is opposite to a proportion number, so certain number times the displacement, okay? And this constant is going to depend on the time period of the oscillations, and it will increase with the number with the decreasing time periods, okay? So if I have a higher frequency, then that means that my acceleration is bigger, okay? If I have a higher frequency, then my time period is smaller because it takes me less time for me to get the complete cycle of my oscillatory motion. So from now on, we are going to look and see these two formulas here many times, every time that I will be telling you about simple harmonic motion. Acceleration will be, and this is the general formula, minus, and then the constant is going to be 2 pi f squared times x, where x is the displacement, okay? So 2 pi f, this comes because I have a kind of a circular motion, okay, where f is my frequency, and is my frequency that can be also viewed as 1 over t, where t is the time period, okay? A there stands for acceleration. Again, coming from circular motion, and go on that playlist if you don't know how this relates to this, my acceleration can also be expressed as minus omega squared x, where again x is the displacement, and my omega square is 2 pi f, which is the same as, since f is 1 over t, it's going to be equal to 2 pi over t, the time period, and omega stands for the angular frequency, okay? And the same is kind of explaining here as well. So my acceleration in simple harmonic motion is always going to have this form, which can be viewed as this form, okay? So that means that if you want to prove that an object has or is oscillating in a simple harmonic motion, you just need to prove that the acceleration takes this form. On the other way around, if you get an acceleration within this form, then you can say in your questions that the object oscillates in a simple harmonic motion, okay? So that's all for today, or for this lesson. There are some questions here for you to train using the formulas that I gave you, or using the stuff that I told you about today. And if you want to attempt these questions, which you should, these are going to be the answers, okay? As always, if you have problems, come and speak to me directly, or send me an email or a message. And I hope this made sense for you. And take care. See you soon. Bye.